This will be the second of 3 videos on distributions. We'll pick back up where we ended on the first one.
Is going to be equal to 1 or 100%, and that's why we can calculate these probabilities from these distributions. The binomial is going to be a fixed number of trials. The trials are independent. You flip the coin, next time you flip the coin, it doesn't matter what you flip the first time, the second one is going to be independent of that. The two outcomes are classified into 2 categories. Bicycle's got 2 wheels, so bi means 2. Tricycle's got 3, so it's got, it's got 3 wheels. So binomial, there's 2 values, 2 nominal values. It can be either this value or that value. The probabilities remain the constant for each trial. You don't switch them between trials. You flip a coin once, it's 50-50. You flip it again, it's 50-50. You don't keep switching back and forth. The mean for the binomial is going to be NP. And the variance is going to NPQ, where Q is going to be equal 1 minus the p-value. Okay. So let's go through and calculate the mean, the variance, and the standard deviation of a binomial distribution for n is equal to 100 and p is equal to 0.3. So the mean, 100 times 0.3 is 30. Okay? The variance, NPQ. 100 times 0.3 times 0.7. Okay, where does 0.7 come from? Remember that Q is equal to 1 minus P. So since P is 0.3, 1 minus 0.3, that tells us that Q is equal to 0.7, which is what we have here. And then if we wanted to calculate the standard deviation, that's going to be the square root of the variance. The square root of 21 is 4.6. Okay? With the Poisson, the occurrences must be random, independent, and uniformly distributed. The standard deviation is going to be the square root of the mean. A little bit different than it was with the binomial, but it's a different distribution, so that's okay. The probability of x occurring is going to be the mean raised to the x divided by x factorial over e to the minus u. E is going to be this value, 2.71828. E is another value. It's an irrational value. It's one that mathematicians have discovered to have a lot of uses, and so they've given a specific name to it. It's a natural log. Like pi is equal to 3.1416, whatever it is. The same thing. It's an irrational number. It never repeats. E is also a irrational number. It never repeats. Anytime you see E in a calculation, it means put in 2.71828. Okay. I've also done a video on math symbols, and in that video I talked about 0 factorial. 0 factorial is always going to be equal to 1. Now, you can look at that and you say it doesn't make any sense. I don't know why that is. Trust me. I can show you how it works. I can show you that this is a true fact. But for right now, all you need to do is just say, anytime you see 0 factorial, that's going to be equal to 1. Okay? Ask any of your mathematician friends what 0 factorial is, and they'll tell you it's equal to 1. Okay, so why do we use the Poisson? Well, we can use the Poisson to approximate the binomial. This is useful when n is greater than or equal to 100, and the NP is less than or equal to 10. Now, why is that important? Well, in your book, you'll notice that you have a table of binomial probabilities. Okay? But this table is a couple of pages long, and it only goes up to 15. So if you're going to go through and to calculate a probability with the binomial above 15, you can't use the table in the book anymore. You're going to have to use something else. You're going to have to calculate it out by hand. And what we found out that it's much easier, trust me, much easier if we go through and we use a formula such as this one. So if you do find yourself in a situation where you have to calculate make an approximation or calculate binomial probabilities, the Poisson is a good one if it meets these criteria. Let's talk about the normal curve. Typical bell-shaped curve, symmetrical, mirror image based when you divide it down by the mean. The standard normal has got a mean of 0 and a standard deviation of 1. Again, it's the one that sort of looks like this. 0 here, standard deviation of 1. Okay, you get the idea there. Okay, the uniform distribution. Classic example here is rolling a dice, where each outcome has a probability of 1 out of 6. Don't confuse that with rolling a pair of dice, because the probabilities of rolling a 7 with a pair of dice is greater than the probability of rolling a 12. If you roll a 12, you can only get that with a 6 and a 6. If you roll a 7, you can get a 1 and a 6, a 2 and a 5, a 3 and a 4, and then you can keep going, a 4 and a 3. This is the first dice. This is the second dice, a 5 and a 2, and a 6 and a 1. There's 1, 2, 3, 4, 5, 6. There's a 6 out of 36 chance of rolling a 7, and there's a 1 out of 36 chance of rolling a 12. So that distribution just works, is normal, is a uniform distribution just for rolling a single dice. Okay, the normal is an approximation.
Let me break in at this one. This is the end of the second session of this video. And just right quickly, let me go back over something that I want to show you just right quick. This is going through and rolling the dice again. And you can see that if this is one die, the result of one die, this is the result of the other die, then you can get a 7 by a 6 and a 1, 5 and a 2, 4, 3, up through this diagonal. So there are 6 possible ways out of 36 to get that. And then over here, there's only one way to get a 12 and only one way to get a 2. So again, hopefully that's helpful to you, and we will conclude this second part, and then we'll start with the third part in just a minute.